Namaskar. Today we will discuss about the regional metamorphism of Peltic rocks. We have already discussed in our part 1 about the regional metamorphism of Peltic rocks, about the geolite phases as well as green schist phases. Now, in part 2, we will discuss in detail about the amphibolite phases and gammolite phases. What are the changes mainly in Peltic rocks? Introduction. On the basis of pressure and temperature, we can divide the metamorphic phases into 3 types, mainly phases of low pressure, phases of intermediate pressure and phases of high pressure. Maya Siro originally recognized 3 different phases series. First, a geolite, prehenite, pumpelite, blue schist eclogite type. Second, a typical Barrovian type characterized by green schist, epidote amphibolite, gammolite type characterized by paragenesis of kyanite, sillimanite type. And third, an Abukama type of green schist, amphibolite, gammolite characterized by paragenesis of andalusite, sillimanite type. Fay et al. In 1958 divided the metamorphic phases into 2 types on the basis of pressure, that is contact metamorphics where pressure is less than 4 kilobar, and regional metamorphism where pressure is more than 4 kilobar. Regional or Barrovian metamorphisms covers large area of continental crust typically associated with mountain ranges, particularly subduction zones or the roots of the previous eroded mountains. The regionally metamorphosed rocks occur during anorogenic events, the collision of 2 continental plates or iceland arcs with continental plate produce the extreme compressional forces required for the metamorphic changes typical of regional metamorphism. The phases of intermediate pressure or Barrovian type in order of increasing temperature and pressure of metamorphism, that is first geolite phases, second green schist phases, third amphibolite phases and fourth is gammolite phases. Metamorphic zones and subphases. The amphibolite phases are divided in 4 different zones, that is your stolite zone, stolite almandine subphases, kyanite zone, kyanite almandine subphases, sillimanite muscovite zone, sillimanite muscovite almandine subphases and sillimanite orthoclase zone, that is also known as sillimanite orthoclase almandine subphases. Amphibolite phases. The appearance of stolite is indicator of upper limit of the green schist phases and beginning of the amphibolite phases. The diagnostic mineral assemblages restricted to this phases are hornblende, plesioclase, anorthite 15% plus minus epidote or hornblende, plesioclase, anorthite 15 plus minus garnet. The characteristic minerals are stolite, gracilorite, almandine, diopside, cummingtonite, anthophyllite, sillimanite, orthoclase, etc. Disappearance of andalusite and cauderite distinguish Peltic assemblage of the amphibolite phases from those of the hornblende hornfels phases of low pressure thermal metamorphism. The presence of stolites along with kyanite is a diagnostic of this zone. Stolite appears in these rocks that are richer in Al2O3 and FeO and poor in alkalis as shown by the Hosek in 1967. Kyanite plus chloritoid give rise to stolite plus quartz plus water. This reaction was carried out by Richardson in 1968, Hosek in 1969 at 540 degree centigrade 4 to 7 kilobar pressure. The next reaction is your chloritoid plus quartz give rise to stolite plus garnet plus water, nearly 30 degrees centigrade higher than one reaction by Gongley in 1969. The next reaction is your chloritoid plus muscovite plus minus almandine give rise to stolite plus biotite plus quartz plus water. The reaction carried out by Hosek 1969, Richardson 1968 at 540 degree centigrade 4 kilobar, 565 degree centigrade 7 kilobar. The assemblages are, first assemblage, kyanite, stolite, plus minus muscovite, plus minus microcline, plus minus plesioclase, plus minus quartz. That is also known as kyanite stolite schist. Second assemblage, stolite, almandine garnet, plus minus muscovite, plus minus microcline, plus minus oligoclase, quartz, stolite, almandine schist. Third assemblage, stolite plus almandine, plus minus biotite, plus minus muscovite, plus minus microcline, plus minus plesioclase, plus minus quartz, also known as stolite, almandine, biotite schist. Now, fourth assemblage is your kyanite, stolite, biotite, muscovite, microcline, plesioclase, plus minus quartz, also known as kyanite, stolite, biotite schist. Fifth assemblage is your kyanite, biotite, muscovite, microcline, plesioclase, quartz, also known as kyanite, biotite schist. Now, the sixth assemblage is your almandine, biotite, muscovite, plus minus microcline, plus minus plesioclase, plus minus quartz, is also known as almandine, biotite schist. Seventh is your biotite, muscovite, microcline, plesioclase, quartz, also known as biotite schist. Eighth is your muscovite, almandine, biotite, epidote, plesioclase, quartz, also known as muscovite, biotite, garnet schist. Now, next zone is your kyanite, almandine zone. When stolite reacts with quartz in the presence of muscovite, form kyanite plus biotite plus almandine. The disappearance of the stolite represent the beginning of kyanite almandine zone. The reaction is stolite plus muscovite plus quartz give rise to kyanite plus biotite plus minus almandine plus minus water. This reaction was carried out by Hosek in 1969 at 567 degree centigrade 2 kilobar, 675 degree centigrade 2 to 5 kilobar. Stolite, quartz, kyanite, almandine plus minus water. This reaction was carried out by Richardson 1968 at 700 degree centigrade between 4 to 7 kilobar. Thus, the appearance of stolite provides difference between stolite zone and kyanite zone. The assemblages are 1. The kyanite almandine plus minus muscovite plus minus microcline plus minus plesioclase plus minus quartz, that is also known as kyanite almandine schist. Second assemblage is your kyanite, almandine, biotite, muscovite, microcline, plesioclase, quartz, also known as almandine biotite schist. Third is your almandine, biotite, muscovite, microcline, plesioclase plus minus quartz, is also known as almandine biotite schist. The fourth assemblage is your kyanite, biotite, muscovite, microcline, plesioclase plus minus quartz, also known as kyanite biotite schist. Fifth assemblage is your biotite, muscovite, microcline, plesioclase plus minus quartz, also known as biotite schist. Now, the next zone is your sillimanite muscovite zone. The mineral assemblages of the sillimanite muscovite zone are similar to the kyanite zone. Here, kyanite is replacing by the higher temperature aluminosilicate polymorphs sillimanite. Kyanite give rise to sillimanite. Rocks are no more schist. Now, the schists change into gneisses. The assemblage One is sillimanite, almandine, plus minus muscovite, plus minus microcline, plus minus plesioclase, plus minus quartz, is also known as sillimanite almandine gneiss. Second is your sillimanite plus minus almandine, plus minus biotite, plus minus muscovite, plus minus microcline, plus minus plesioclase, plus minus quartz, also known as sillimanite almandine biotite gneiss. Now, the third assemblage is your almandine plus minus biotite, plus minus muscovite, plus minus microcline, plus minus plesioclase, plus minus quartz, also known as almandine biotite gneiss. The fourth assemblage is your sillimanite, biotite, muscovite, microcline, plesioclase, plus minus quartz, also known as sillimanite biotite gneiss. The fifth assemblage is your biotite, muscovite, microcline, plesioclase, plus minus quartz, also known as biotite gneiss. Now, the next zone is your sillimanite orthoclase zone. Muscovite, which was present throughout the range of metamorphic phases from green schist to sillimanite muscovite zone of amphibolite phases, now become unstable. It is with this breakdown of muscovite that the sillimanite orthoclase zone R begins. The following reaction take place: muscovite plus quartz give rise to orthoclase plus sillimanite plus water at 595 degree centigrade 1 kilobar, 640 degree centigrade 2 kilobar by Day and Chatterjee 1974. Orthoclase KAlSi3O8 polymorphs microcline is also transferred to higher temperature orthoclase. Furthermore, under the pressure temperature condition of this zone, partial melting or anastasis of peltic rocks take place, as demonstrated experimentally by Tuttle and Bowman in 1958 and Winkler 1974. The assemblages are: first, sillimanite, almandine, orthoclase, plesioclase, quartz, also known as sillimanite almandine gneiss. Second assemblage, sillimanite, almandine, biotite, plus minus orthoclase, plus minus plesioclase, plus minus quartz, also known as sillimanite almandine biotite gneiss. Third assemblage is your almandine, biotite, orthoclase, plesioclase, quartz, also known as almandine biotite gneiss. The fourth assemblage is your sillimanite, biotite, orthoclase, plesioclase, quartz, known as sillimanite biotite gneiss. Fifth assemblage is your biotite plus minus orthoclase, plus minus plesioclase, plus minus quartz, or also known as biotite gneiss. Now, the next higher zone is your gammalite phases. The gammalite phases is very high grade metamorphic rock phases in which muscovite is replaced by potash feldspar and coexist with Al2SiO5 polymorphs, that is sillimanite. Characteristic minerals: presence of hypersthene, garnet, grasular less than 20%, pyrope nearly 55%, potash feldspar, sillimanite is indicating the gammalite phases with all amphiboles are absent. Perthite is a characteristic of gammalite phases. The important reaction in gammalite phases are Mg anthophyllite give rise to hypersthene plus quartz plus vapor. Second reaction, biotite plus quartz give rise to orthopyroxene plus garnet plus potash feldspar. Third reaction, biotite plus sillimanite plus quartz give rise to garnet plus potash feldspar plus vapor. Zones oblique subphases, all these reactions involving hornblende, anthophyllite, biotite are divariant on according of varying Fe and Mg ratio and also condition of water P water pressure less than P total. That is, the reaction start at certain temperature, but all equilibrium phases will be present over a temperature range until with rising rate. Hornblende, anthophyllite, biotite disappear. Thus, two subphases, hornblende gammallites and pyroxene gammallites, are recognized. First is your hornblende gammallite subphases in which hornblende and biotite are present with water. Second, pyroxene gamma-lite subfaces with absence of hornblende and biotite or less amount of water. Hornblende gamma-lite surfaces, the mineral assemblages, first the sillimanite, almandine plus minus potash feldspar plus minus plagioclase plus minus quartz. This is also known as sillimanite almandine gneiss. Second, the sillimanite plus almandine plus minus inesitite plus minus potash feldspar plus minus plagioclase plus graphite plus minus quartz, also known as sillimanite almandine inesitite gneiss or condylite assemblage. Third important is your almandine plus minus inesitite plus minus potash feldspar plus minus plagioclase plus minus quartz, also known as charnockite, garnet bearing charnockite. The fourth is your sillimanite plus biotite plus minus inesitite plus minus potash feldspar plus minus plagioclase plus minus quartz, also known as sillimanite biotite inesitite gneiss. And the fifth, sillimanite biotite potash feldspar plagioclase plus minus quartz, that is also known as sillimanite biotite gneiss. The sixth is your biotite plus minus hypersthene plus minus potash feldspar plus minus plagioclase plus minus quartz, or it is also known as biotite inesitite or charnockite, garnet free. Inesitite plus potash feldspar plus minus plagioclase plus minus quartz is also known as acid charnockite. The eighth is garnet, potash feldspar, plagioclase feldspar plus minus quartz is a typical gamma-lite rocks, that is known as garnet gneiss or leptinite. Now, the next important higher grade is your pyroxene gamma-lite subfaces. The assemblages are first sillimanite, almandine garnet plus minus potash feldspar plus minus plagioclase plus minus quartz, sillimanite almandine gneisses. Second is your sillimanite almandine plus minus inesitite plus minus potash feldspar plus minus plagioclase plus minus graphite quartz is known as condylite. The third is your almandine plus minus hypersthene plus minus potash feldspar plus minus plagioclase plus quartz is also known as almandine hypersthene gneiss or garnet bearing charnockite. Fourth assemblage is your sillimanite plus minus hypersthene plus minus potash feldspar plus minus plagioclase plus minus quartz is also known as sillimanite hypersthene gneiss. The fifth assemblage is your hypersthene oblique inesitite potash feldspar plagioclase quartz is garnet free charnockite. Conclusion: the course content on regional metamorphism of Peltic rocks begin with the introduction, followed by the description of introduction, characteristics of Peltic rocks, metamorphism of Peltic rocks with a detailed comparison of geolite to gamma-lite phases with the help of ACF, AKF and AFM diagram. Important reaction during prograde metamorphism of Peltic rocks, and also observe the important changes in Peltic rocks. Thus, on the basis of the detailed study of different subphases and also with the support of experimental data, we can conclude that during prograde metamorphism of Peltic rocks, different rocks are formed like slate, phyllite, schist, gneiss and Peltic gamma-lites. If suppose we compare the regional metamorphism of Peltic rocks part 1 and part 2 both, we can see how the sedimentary rocks, that is shell or siltstone, change into slate, phyllite, schist, gneisses and latterly the Peltic gamma-lites. With the help of ACF mainly for the geolite phases and AFM for green schist, amphibolite and gamma-lite phases rock, we can observe mainly in apex, that is A corner, the kaolinite change into pyrophyllite, pyrophyllite change into kyanite and latterly the kyanite change into sillimanite. This is the major change in peltic rocks, especially how the clay minerals change during metamorphism into sillimanite with the effect of high P and T. Similarly, the chloride change into biotite and laterally the biotite change into almandine garnet. And if suppose you will compare the A and C corner, the epirode change into plagioclase with anorthite percent 15 and laterally this anorthite percent change into up to 40% in amphibolites and gammalite phases. Similarly, we can see the F corner which normally change from talc to anthophyllite and laterally anthophyllite change into hypersthene. So, in whole comparison we can see how a peltic metamorphism occurred with effect of pressure and temperature. Usually, one major question is asked in all the examination, give a detailed account of regional metamorphism of peltic rocks or give a detailed account of prograde metamorphism of peltic rocks. In that case, we have to compare only the peltic rocks metamorphism right from geolite up to gammalites with the help of AFM diagrams.